equation, row echelon form, those kind of stuff. Okay. So this week we are going to focus more on matrix. Okay. Not like a Keanu Reeves movie. Okay. It's easy. Okay. As you have already learned from last week. Okay. We can write the coefficient of the system of linear equations into matrix, right? So as a result, okay, the matrix looks like this, okay. So it's a n times n, okay, where n represents the number of rows, okay, n represents the number of columns, okay. So I even mentioned to you last week that, okay, the translation of the row and the column between Taiwan and China are different, okay， 刚好颠倒，对不对？就是比如说一个是这个 column 说是列，那 row 说是行，那 like in China they say these things different, okay? So okay. So we are going to focus more on the matrix. So, so there are a lot of the property of the matrix that we need to discuss today, and some operations we could apply on the matrix. Okay. For example, okay, how do we check two matrices are equal? Okay. If we say two matrices are equal, okay, first, they have to have the same size. Okay, it's A, matrix A and matrix B, they have to have the same number of columns. They have to have the same number of rows. So that's the first thing, okay. The second thing is, for every corresponding element, they should be the same, okay? So these two have to be, true for, for two matrices to be considered equal. So for example, okay, we have A, B, C, and D, okay? Where you can see that A, okay, is 2 columns, 2 rows. Okay, 2 rows, 2 columns. And B, C obviously have the different size. Okay, and D has 2 columns, 2 rows as well. But for A and D to be the same, okay, because the corresponding elements, the other 3 are good. So the only one is the x. So in order for A and D to be equal, okay, x has to be 3. Okay, and for B and C, they have the different size. Okay, even though they, this is like 2 by 1, 2 rows, 1 column. This is 1 by 2, 1 row, 2 columns. So their size will be different, even though they have the same content. Okay. So just some example to show you, okay, how the matrices are considered equal. Okay, and obviously we can also do certain operations on matrix, such as addition. Okay, if A and B are matrices of the same size, okay, then we can add these two matrices together, okay, the resulting matrix will be, again, with the same size, but each element will be the sum of these two, the corresponding location of these two matrices. Okay, so for example, okay, here you can see we have 3 by 2. Okay, this is 3 by 2 matrix. This is 3 by 2 matrix. So they have the same size. Okay, so if you add them up, okay, you can see we actually try to add every corresponding element together in here. So this is the result. And I think this is pretty straightforward. Okay, and the matrix has scalar multiplication as well. Okay, so for a matrix, okay, if C is a scalar, which means it's a real number, so you can, multiply this scalar to this matrix. Okay, as a result, like every element in this matrix, will be multiplied by this constant C. Okay, and we can have subtraction as well. Basically, like we define negative A first. Basically, it's a -1 times A, and A minus B will be A plus negative B. Okay, so it will be AI. Basically, it's matrix of the same size, but every element becomes like Aij minus Bij. Okay, so here's the example. Okay, for the scalar. Okay, we multiply this matrix by 3. So as a result, it becomes like this. Okay, for subtraction, I think you get the idea. Okay. So far, okay, all this discussion, okay, does it remind you anything? In high school, you learn something called vector, right? 向量. Okay. So matrix, a lot of these properties are similar to vectors, right? The only difference is that vector, depends on how you write it. It's a row, one row or one column, right? Okay. But you can imagine matrix as like a more generalized version of a vector. Okay. But this one is different. This one is different. I mean, for vector, we don't have that. Okay, this is the matrix multiplication. Okay, it's not like scalar multiplication, but here we are multiplying two matrices together. Okay, so there are two things that we need to talk about. First, okay, it's not that every pair of matrices can be multiplied together. Okay, they have to have the appropriate size. What I mean by appropriate size, okay, say if the first matrix is of size n by p, the second matrix has the size p by n, then we are able to multiply them. So in other words, okay, the first matrix, okay, the one in the front of the multiplication, okay, its column, its number of column has to match the second matrix number of rows. Okay, they have, you see like first matrix has like p column, second matrix has p row. Okay, and the resulting matrix will be n by n. So you will have like n number of rows, n number of columns. Okay. As for how we obtain this Cij, it's going to be like Cij is going to be like a multiplication of Aik Bkj. Okay, where k runs from 1 to p. Okay, we add them up. That's the result. And if you look at this as a picture, okay, it's going to look like this. Okay, so here, okay, is the matrix A, here's matrix B. So this the ith row multiplied by j's column, because this one has a p columns, this one has p rows, right? So we have exactly same number of elements. So we can multiply them one by one and add them up together to get an element Cij here. Okay? So we do this for every Cij, basically. Okay? And one important thing to mention in matrix multiplication is that the matrix multiplication is not commutative. Okay, what do we mean? It's like A times B is not necessarily the same as B times A. Is there such a case? Yes. Yes. Okay, some matrices, if you multiply them, and you switch their order, yeah, and they happen to be the same result, but this is not the case in for most of the multiplication. Okay, not only that, if you can multiply A to A and B, sometimes if you switch the order, you cannot even do the multiplication because the size, okay, is not right. Okay, remember, matrix multiplication has to make sure that the first matrix, the number of columns has to match second matrix, the number of rows. Okay, so for you to switch the order, well, the n is not necessarily the same as n, right? So anyway, here we have an example. A to be this one, B is this one. Okay, A is basically 3 by 2, right? 3 by 2, and B is 2 by 2. So yeah, the size is okay because the first matrix has 2 columns, the second matrix has 2 rows. So that their size are okay to multiply. Okay, and the C, okay, will be basically the size will be 3 by 2. Okay, it will be we get number of rows from the first matrix and number of columns from the second matrix, and the Cij, okay, the result will be this one. For example, let me do one. Okay, for example, C11 will be the first row. The first row multiplied by the first column. So -1 times -3, so which will be 3, plus 3 times -4, so which is -12. So it's a -9. Okay, so it's not -9 here. Okay, you get the idea for the rest of the elements. So the result looks like this. So this should be taught in high school, right? You should have learned this in high school. So, okay, so I can probably speed up a little bit. Okay, so remember the connection between the matrix and the system of linear equations. Okay, so say we have a system of linear equation like this. Okay, we can express them in 2 ways. First, we can express them as the linear equation of vectors. These are the vectors. Actually, when we talk about vector, okay, in linear algebra, we usually consider them as a column vector. Okay, so basically x1 is 147, right? x2 is 258, and so on. Okay, so it looks like, so you can either consider the system linear equation as the one equation, one linear equation for vectors. Or you can consider this one as like the matrix times this column vector x1, x2, and x3, and the result is this one. Okay, why? Because you multiply like by using the matrix multiplication. This row times this column, you get the first one. The second row times this column, you get the second one, and so on. So it will be equivalent to our system. Okay, so basically like this represent two views of the system linear equation. This is very important because like sometimes this thing will help you to connect the left view. We need to connect this left view and the right view. Otherwise, like some of those like material, after like in the future, I mean, you will not be able to understand. So, okay, we represent this one as this, as the right hand side here. Okay, and this one obviously is, as I said, there are two views. Okay, so this one is the same as that one. Okay. So keep in mind, okay, the matrix, okay, can be considered a combination of some column vectors. Okay, or putting it another way, okay, the sum of a linear combination of like vectors can be considered a matrix multiplied by a column vector. Okay, keep that in mind. Okay. Then more property about matrix like operations. For example, for addition, okay, we have commutative property. Okay, in other words, like we can switch the order, the result doesn't matter. Okay, it will be the same. Okay, and we have associative property for matrix addition. In other words, A plus like parentheses B plus C will be the same as you add A plus B first and then plus C. Okay, or like a scalar multiplication. Okay, satisfy the CD times A equal B to like C times D times A. Okay, this is also considered as like associative property. Okay, and in particular for scalar multiplication, okay, one is identity. Okay, now if you multiply 1 to A, you get A. Okay, you change the A matrix. Okay, and then we have distributed law. Okay, like a scalar C times A plus B, you can distribute this C into CA plus CB. I mean, it will be the same. Or like a C plus B times A. Okay, again, the distributed law. Okay, apply both ways. Okay, it will be CA times BA. Okay, CA plus BA. Sorry. So basically, like these are like the properties that you need to know, and these properties are pretty straightforward to verify. Okay, for example, for like A plus B equal to B plus A, obviously like because you consider like the ith row J's column, okay, in A plus B, okay, it will be Aij plus Bij. So in just basic like addition, obviously it will be the same as Bij plus Aij. So it will be equivalent to B plus A parentheses Ij. So this problem can be proved like easily, okay? And we can also prove like distributed law of C plus D times A, okay? Because for every element, okay, for I row J column, okay, the element I row J column, it will be C plus D times Aij. From here to here, it's according to the property of scalar multiplication, the definition of scalar multiplication. And then, obviously, because now we are dealing with numbers, these three things are numbers. So we can, the number, distributed law apply to the number, so it becomes like this. When it becomes like this, okay, so CAIJ is C times A, parentheses IJ, according to the definition. And DAIJ is this one. Again, according to the definition, so we can write it back like here. Okay, so every time we talk about proof, it always comes back to the definition. Okay, and you can try to prove the other stuff here. For example, like the distributive property for C times parentheses A plus B. Okay, and give it a shot. I mean, just try to, get yourself familiarized with like a proof. I know like in discrete math, you learn how to prove things like in that class. In this class, you are going to see more proof. Probably not as much as like discrete math. However, we still have like quite a lot of proof, okay, to talk about. So, and we could have a zero matrix. Okay, zero matrix is represented by big O M N. It is like a M by N matrix consists entirely of zeros. Okay. So if every element is a zero, when you add A to this zero matrix, obviously, it doesn't change A. Okay, so you have that. Or if A cross negative A, okay, every element cancel out each other, so you obtain O, like an O matrix, zero matrix. Okay. Or if CA equal to zero, then either C is zero or A is zero matrix. Okay, this is very obvious, right? So we could also have a matrix equation, okay? For example, like if you have 3x plus a equal to b, where a is like this, b is like this, then basically, okay, 3x will be, like b minus a, right? And then x will be, will be like this. And then you multiply this both sides by 1/3, you get x, right? So it's going to go to, x is going to be this one. And b minus a, okay, will give you this. And each element multiplied by 1/3, you have this. So this is your a, sorry, x, this is your x. Pretty easy, right? Okay. I mean, in college, this type of operations, like, is pretty much given, okay? Like, you should be able to do this, like, very easy. And then, okay, the matrix multiplication, A, B, and C are matrices with the right sides. In other words, like, they can be multiplied together. Okay, they can be multiplied together. Like, when they put together. Okay, so we say, and C is a scalar. So A times B times C first. Okay, it will be the same as A times B first and then times C. Okay, this is an associative property for matrix multiplication. Okay, this is very special. Okay, remember the matrix multiplication, the commutative law does not apply, but the associative property is there. Okay, and we also have distributive property. Okay, A times parentheses B plus C will be the same as A times B first plus A times C. Okay, and this distributive property, okay, applies on both sides. So A plus B times C will be the same as AC plus BC. Okay, you see, like we carefully maintain the order here. Okay, I mean A times B plus C. Okay, like you cannot, A has to appear in the front. Okay, for both terms. Same thing, like when C is the second term, is a later term, it appears on like these two terms, like both has like the second operator. Okay, and also like the C, the scalar times A plus A times B. Okay, you can multiply this scalar to A first, or you can multiply the scalar to B first. Okay, it doesn't change the fact. It doesn't change the result. Okay, so this property, of course, like they need to be proved. Okay, just like the previous properties. Okay, of course, like but we don't have time to prove every property. Okay, we will just use the distributive property as an example here. But for you, I will highly recommend you try to prove every property by yourself. Okay? So for distributive, actually one of the distributive properties, okay, A times parentheses B plus C. Okay, we want to prove this one equal to AB plus AC. So first we need to consider every element. Okay, ij, ith row, ith row, jth column. Okay. Whether or not, I mean, this one is the same as this one, ij, right? If every element, corresponding element are the same, then obviously these two sides will be the same. I mean, you may argue, okay, yeah, but when you talk about like a matrix, when you say two matrices are equal, not only the corresponding element have to be the same, I mean, they have to be the same size, right? But the same size fact is a given, because like you see like what should I say, like if this matrix can be multiplied, obviously the number of columns in A should be the same as number of rows for B and C, right?